there questions from yesterday? Okay, so let me begin. So I'll begin by reminding you where we reached yesterday. So our goal was to calculate this Green's function, okay, whose definition is the vacuum expectation value of time ordered product of operators. And what we saw was that this is given by the following path integral. Okay. In defining this, we have to be a little careful about choosing the time axis not exactly along the real axis but slightly tilted. Okay, that is the 1 minus I epsilon multiplication that we discussed, and today we will see where that plays a role in the actual calculation. Okay, because only under that assumption that this is equal to this. Okay, that the time axis is not along the real axis but slightly tilted. Okay. So our goal today will be to try to develop techniques for calculating this object. To do that, let me just introduce a few notations. Okay, in particular the concept of functional differentiation. So suppose you are given a function phi. X for us stands for x and t. So suppose you are given some function phi of x. Then a functional f of phi this generates a number for given function phi of x. So in general, it contains information about a full function, which means the value of phi at all x. And given that information, f of phi generates a number. Okay. This is different from functions, where a function is a set of what a function does is that it generates a number if you are given the value of the arguments. Right? If it's a function of n variables, then once you specify the n variables, you have a number. Okay. Functional requires specifying infinite number of variables because you are actually specifying a whole function. Okay. But this you can also think in terms of functions by discretizing. Okay. So if we discretize, once you discretize, in which case you replace phi of x by this phi of I0, I1, I2, I3. Okay, these are the lattice points. Then a function of phi can be sort of an ordinary function of all of these variables. Okay, because you are replacing the function, the continuous function phi of x by a collection of numbers, which are these, and then the functional becomes an ordinary function of these variables. So let's look at some examples. S of phi, right? So we wrote down the expression for the action. This is a function on a phi, right? Because given the whole function phi, S of phi tells you gives a number, right? Which is the integral of that appropriate Lagrangian density. So this is a function. Now suppose take some fixed point y, some space-time point y, and consider phi of y. Okay, y is some fixed given space-time y. So is this a functional of phi?
Which one?
Phi of y. Is this a functional of phi? No. So what does the functional supposed to, what should the functional do? It should generate a number for a given function phi of x. Right? Suppose I give you phi of x. Okay, a function e to the x square. Right? Does this generate a number?
Yes.
Point y.
Yes. So to fix y, right, this is a number, right? So this is also a functional. This is also a functional of phi. So not all functionals need to have integrals over phi, right? Because a functional should can depend in general on the value of the function at all points, but it need not. Right? You can have a functional which depends on the value of the function at one particular point. Okay, as long as you are given a rule that gives you a number for a given function, that's a functional. Is this point okay?
But we have to specify then how to choose that point y.
No, I have given you y, right? The origin, for example. Right? That's why I say y is given. I have given you y, right? Then phi of y is a function. Yeah, if you choose y to be different, suppose instead of taking the origin, you take the y to be another point, right? It's a different functional. Right? Because it gives a different number for the same function phi of y. Is that clear?
You can define it a delta function.
No, I'm not going to define any delta function right now. Right? All I'm saying is that anything that gives a number for a given function is, according to this definition, a functional. Okay? If we use the discretized version, okay, suppose you use a discretized version, okay, where a functional is a function. Okay? So suppose y is given by h1. So x is h1 j1, h2 j2, h3 j3, and delta j0. Okay, so this is the time coordinate of y and these are the space coordinates of y. So if you are given y to be this, right, then what is f? Now it should be an ordinary function, right? This is supposed to be some function of all these variables, right? Okay. So what is this function? Phi of y. How will you write in this notation? Yes, it's not very complicated question, right?
Put the arguments in the bracket.
Just put the argument.
Put the argument there. So this is phi j1, or the way I have it written, j0, j1, j2, j3. This is equal to one of the components of phi, right? But it's still a function of x and y, right? X is a function of x and y, right? It happens to be independent of y, but nevertheless, x is a function of x and y, right? If you are given two variables x and y, x is a specific function of those, right? So this is that kind of function, right? You are given infinite number of variables, but this function depends on only one particular variable. Okay? Nevertheless, if you are given this infinite number of variables, okay, this is a number. Is this okay? Yeah. So I was trying to explain that why, if y is given, right, why phi of y is a functional. Okay. First, you use a definition that is given here, that given any function, it should give a number, right? And this does give a number if you are specifying the function phi of x. Right? Take this whole function phi of x and evaluate it at the point y. Right? So that's a number. Right? So it's a functional in that sense. Okay. But then I said that functional can also be written as an ordinary function if you discretize. right? But it's an ordinary function of many variables, right? Infinite number of variables. Okay. So if you want to see in this picture what happens, right? Then what is the corresponding function f here, right? F to begin with could be a function of all of these variables, right? Okay. But the specific function that represents phi of y, okay, is this one. Okay, but this nevertheless is a function of all these variables. Right? It depends on only one variable, but it's just independent of all the other variables. Right? That's still a function. Okay, when a constant is a function, right? A constant which doesn't depend on the variables is still a function. Okay, because it gives a number for a choice of the variables, right? Because this constant doesn't depend on the choice of the variables, but nevertheless it gives a number. Okay, so with this now we can define functional differentiation. So suppose f of phi is a functional. Functional I write this one. The functional differentiation is like derivative with respect to some particular point, value of the function at some particular point x. Okay, functional differentiation, okay, what it should generate, okay, let me say what it should generate. It should generate a number, okay, if we are given the function phi, okay, and if you are given this point x. Okay, so it's a function of x and a functional of phi. Okay, so knowing the, if you want to know this, okay, you have to know two informations. One is what function it is, the second one is what the argument is. Is that clear? Okay, so this will define by discretizing. Okay, we think of the function as this function of many variables, the function as a function of many variables. Okay. And similarly, let's suppose that x is given by h1 i1, h2 i2, h3 i3 and delta I naught. Then by definition, this is 1 over h1, h2, h3 delta del f I shouldn't have used I, let me put j. Okay, suppose these are, I is the generic variable I am using. Okay, it's an ordinary derivative of this corresponding function with respect to the variable phi j0, j1, j2, j3. But you have this normalization factor, okay, that I have put in explicitly. Okay, this will just make life convenient, as you will see. Is this definition clear? Okay, so let's see why this is useful. So let's suppose we have f of phi as integral d4x, phi of x, g of x. This is a fixed function. This g of x is a some fixed function of x. I want to calculate delta f of phi say delta phi of y. So how will you calculate this? Okay, we are going to use this definition that I have given here. Okay, so first you have to discretize this side and then use the definition that I have given here. So this I can then write as del phi j0, j1, j2, j3. Okay, assuming that y is given by this. What is the discrete form of this? Well, I should let put the normalization 1 over h1, h2, h3 delta. So what will be the discrete form of this? Integral you have to write as sum, right? So we put h1, h2, h3 delta, sum over I0, I1, I2, I3, phi I0, I1, I2, I3, j I0, I1, I2, I3. And now you see that this factor cancels this factor over here. Okay, this is part of the definition of the integral. Okay, that's why I have put this in the derivative. So these two cancel, and what you are left with is j, j0, j1, j2, j3. Because only one term here will give a non-zero answer, right? That is when this is j0, j1, j2, j3, and correspondingly pick up j0, j1, j2, j3. Okay. So this I can write as g of x, g of y, right? Because j0, j1, j2, j3 represent the point y. So we learned that this is g of y. Is this clear? Okay. So when we do functional manipulation, okay, we have manipulation with functional derivatives, we are not always going to try to rewrite this in the discrete form, okay, and manipulate. Okay. But if you have any doubt at any stage, you can always go back to the discrete form and check if these manipulations are valid or not. Okay, but we will now learn how to manipulate it without always having to write it in the discrete form. Okay, but you should remember that this is the definition. Okay, if you want to start from the definition and check everything, then this is what you should use. Okay, and then this is just ordinary derivative.
Sir, but
Yes.
is the equation dimensionally like the map between f and the discretized version small f?
Yes.
This, if you see this equation of differentiation,
Yes.
is the dimensions consistent for small f and capital F actually? Because you are having like these,
Well, capital F and small f by definition are the same, so they have the same dimensions.
these are dimensionless factors basically HIs.
No, these have the dimensions of length, right? Because these are time length interval and this is time interval. Right? So the HAs are the lattice spacings.
Yes. So then this equation that capital F is the f of discretized phi's.
Yes, that's here. This is the definition. Right? These I wrote as H1, H2, H3 delta times the discretized phi's. Right? So these would have given a dimension from the x integral, right? Okay, 3 length and 1 time. Right? Those dimensions are here.
No, I was confused about this that when you write functional phi as a function of discretized phi's,
Yes.
so there also must dimension 4 kind of accounting must happen, right? In that, with the previous equation that you wrote, that I guess if I'm
This one. This is one example of that, right? Going from here to here. That is a discretized phi, right? So this d4x became, that dimension went in here. Right? These are the same dimension as phi of x. These are the same dimension of g of x. Right? This d4x in dimension went into the these lattice spacings. Is this okay?
Here also you assume that all phi's are independent of each other.
Yes, that's right. So a function, okay, giving a function means giving its value at all points, right? And in general, we can take the value of the function at different points arbitrarily, right? That corresponds to changing the function. So we are certainly assuming that the phi I0, I1, I2, I3 are independent variables, right? And that's how you define the path integral anyway, right? We independently integrated over each phi I0, I1, I2, I3.
So just one clarification.
Yes.
The delta J0 should be the first.
Well, okay, that depends on how you write it. Since I was writing xt,
Okay.
okay, that's why I wrote delta J0 at the end, but if you want to write time at the beginning, you can put it
Yeah.
at the beginning. Right? It's just a convention that I'm using in the discrete form. I'm writing the J0 at the beginning, right? J0 or I0. But when I write x as xt, then t is at the end, but I could have written it as tx, right? In which case what you said is correct. This delta J0 should be in the beginning. Okay, so hopefully it will not confuse. Right?
Sir,
Yes.
so it will for a given point x and a given function will get a number.
Yes, that's right. So here, for example, I needed to specify this functional. Well, no, not for a given point on x and a given function. For a given point x and a given functional. Okay, that you have to specify what functional this is. See, think of ordinary derivative, right? Ordinary derivative of a function with respect to x depends on what? First, where you are evaluating the derivative, right? That's the point x. But it also depends on what function you are differentiating, right? So the analog of what function you are differentiating is the analog of this functional. Okay, what functional you have chosen, and then which variable you are differentiating with respect to, right? That goes in this x. Okay? So you need to know what functional it is and the x. Right? That's what will specify the derivative. Right? Here, for example, when I wrote this delta f equal to g of y, right? We can see that it depends first of all on what functional you have chosen. Right? If you change this function, if you replace this j by j square, you will get a different result. Right? And it needs information of the point y. Okay, because it's j at y that is giving the functional derivative.
So in this special case, we ended up like the functional derivative does not depend on the function form of phi, but it may happen that functional derivative will depend on.
That's right. Yes. So that's a functional, right?
Yes.
Yeah. So a functional derivative is a functional. Okay, it depends on, maybe I should say, what was the meaning of dependence? That it, you just think in terms of ordinary derivative, right? That if you are given some function of x1 up to xn, right? And you take del del xi, okay, what are the things it will depend on? It will depend on which variable you are differentiating against, right? That I. That analog of that I is this index x over here. Okay. It will depend on the what function you have chosen, right? What function you have chosen, that analog is in the what functional you have chosen. Okay. And then of course it depends on all the other variables, right? What value all the other variables take, right? And that is the information about phi. Okay, what value phi takes at different points. Right? So that's exactly, so if we just think in terms of this, right, I think it will become clear what can the functional depend on. Okay? But the important point is, once you have defined it, it's still a functional. Right? It does depend on the original form of that. You need the form of phi, right? It's a functional. But what functional it is depends on what functional you started with. Right? Just like this one, after you take the derivative, it's still a function of the variables. Okay, that means it's still a functional in that language. Okay. But it also depends on this index I, which is which variable you differentiated against. Right? This analog of the index I is this point x over here.
So once you specify y,
Yes,
j of y is a number.
is a number. Yes, that's right.
Exactly like
In this particular example.
putting x1 in f.
Yes, that's right. So here it so happens that this derivative became independent of x. Right? The analog of the x is the phi here. So maybe I should use another notation. Let me call these betas. Del beta I. Imagine that you have a function of n variables, beta 1, beta 2 up to beta n. Right? When you take the derivative with respect to beta I, right, its value depends on what I index is. Right? Which variable you are differentiating against.
Yeah.
Right? That information is in this x.
Yes.
Okay? The result will depend on what function you have chosen.
Yes.
Right? So that information is what functional you have.
Beta is equivalent to phi in this case. What beta?
Yeah,
what
beta
function
is
of beta?
equivalent to phi. Yes, exactly. Okay? But f is equivalent to that capital F.
Yes.
Right? If it was instead of beta 1 is if it has beta 1 square or beta 1 cube, it will be a different result, right?
Yes. Yes.
Okay? So that f is the analog of capital F.
Yes.
Okay? And the betas are analog of giving the function phi.
Yes.
Is that clear?
Here, the functional form which we have taken has integral form. So this discretization thing that h1, h2, hc deltas cancel out nicely.
Yes.
So if we have not taken it in the integral form,
Yes.
the final answer which now is appearing independent of these factors would also contain h1, h2, hc deltas.
It will not. We'll see. Okay? So you will be happy if I can differentiate phi of y. This doesn't have an integral form, right? Phi of y is a functional. Right? It's not in the integral form. Right? We will differentiate phi of y with respect to phi of x. Right? And we will see what we get. Okay, so it is true that here it looks like some nice cancellation has taken place. Okay? But this cancellation will take place even when it's not in the integral form. Okay, we will see how it comes about.
So also about the dimensionality,
Yes.
I mean f has different dimension from that of phi, right? Because
Yes,
dimension-
f and phi have nothing to do with each other, right?
Yes.
This capital F and small f have the same dimension,
Yes, yes.
right?
So del f, del phi
Yes.
in the definition of the functional
This
derivative. No, not that. In
This
the,
is different dimension compared to this one.
Yes, yes, yes.
Yes,
So
exactly.
it is by definition.
Has this 1 over
Okay.
space-time dimension built in. Okay, this is not the ordinary derivative, right? So functional derivative and ordinary derivative did not have the same dimension.
Yes. Okay.
Sir, why we are not writing f of capital F of phi comma j?
Well, I can write this, write it there. Here, phi comma z.
J.
Well, yeah, you can write it. Okay? Except that j I am thinking of as a constant.
Okay, when we differentiating with respect to phi,
Yeah,
then we will thinking that
j is a constant, but you can write it as a phi of j. It's like a function of, if you have, suppose you have c sine x, right? You could think of it as a function of x, but you could also think of it as a function of x and c. Right? It depends on whether you want to treat c as a constant or whether you also want to treat c as a variable. Right? So I can write f as a function of two variables, but the derivative is taken with respect to phi here. Is this point clear? Okay, now let me keep this definition. From this definition, I think it should be clear that it satisfies chain rules. Delta phi x. Suppose you have two functionals, f of phi and g of phi. Okay? This is delta f of phi, delta phi x times g of phi plus the way to prove it is that you just think of f and g as ordinary functions of the multiple variables, right? In that case, this is just ordinary derivative with this normalization. Right? Ordinary derivatives, of course, will satisfy the distribution property, right? Okay, this is not chain rule, this is distribution property, right? It just distributes over the product of functions. So the ordinary derivative, there will be overall normalization like this. Ordinary derivative will satisfies the usual distribution, and then once you have the derivative, you multiply it back, you absorb this factor into the definition of the derivative, and you will get a functional derivative. Yeah, so because there is only one factor of delta phi on each term, okay, this normalization factor is just trivial, right? It just multiplies everything. Is this point clear? Okay, so now let's go back to what one relation that we derived. Delta phi of x, phi x of f of phi, or right, integral d4y that's what we found, right, using the definition. J is a fixed function. So let's suppose that J of y is delta 4 of y minus w, where w is some fixed set of coordinates. Okay, so this stands for, of course, w0, w1. So then let's see what this equation tells us. It tells us that delta phi x, this integral, okay, when you take g of y to be the delta function, is phi of w. So this is delta 4 of x minus w. Because I just use the form of G. Use this form relation, right? Substitute for G of y this, right? So left hand side is delta phi of x of phi of w. The right hand side is G of x, so just substitute y equal to x here. That's delta 4 of x minus w. Right? So you see that indeed there is no h1, h2, h3 delta, even though there is no integral. Now you can write in the components, okay, if you are surprised by this, right, you can write in the, again in the component form, okay, and you can see where that factor is disappearing, right. It is basically disappearing because the definition of the delta function itself involves that 1 over h1, h2, h3 delta, right. When you write the Dirac delta into Kronecker delta, right, and using the fact that integral of delta and sum over Kronecker delta, right, both do the same job, you will find that there is an extra factor of 1 over h1, h2, h3 delta in the definition of this Dirac delta function, right, in terms of Kronecker delta. Okay, so that's why this is useful, right? That we never have, once you have defined it this way, okay, we can carry out functional manipulations without having to encounter this ever. Is this clear?
So just for clarification, first g of y is defined as the Dirac delta, and this derivative, functional derivative we get is the Kronecker delta. Is that so?
No, both are Dirac delta. I just use the same. See, this is a general relation for any j, right? Okay, I pick j as Dirac delta, okay, and just evaluated both sides. Left hand side, this came from the left hand side of this. Delta phi of x, this integral is phi of w using the Dirac delta form, right? Integral d4y phi of y delta 4 of y minus w, right, is phi of w. Okay. The right hand side is g of x. G of x, just substitute y equal to x here, right? G of x is delta 4 x minus w. So this equation I claim follows from this equation that I derived. this is valid, this equation is valid for arbitrary choice of j, right? We didn't assume anything about j when we derived it. This relation between Kronecker delta and Dirac delta will come if you don't use this equation, okay, but directly try to derive this. Okay, then you will find that you have to use the relation between Dirac delta and Kronecker delta. Okay, if you try to discretize here and try to derive this, right, then you have to use the relation between Dirac delta and Kronecker delta. But once you think of this as a special case of this, you don't need any additional relation between Dirac and Kronecker, right? That is already gone in this.
What I'm thinking is that if we try to evaluate this left-hand side expression from the first principle, will we get a Dirac delta or should we get a...
You will get a Kronecker delta, but which is 1 over h1, h2, h3 delta.
Okay,
Right?
because that was
And that you can show is the Dirac delta. Right? So if you want to derive it from first principles, that's the way this identity only works. Right? But if you derive it as a consequence of this, right, then you consider you never have to use that relation. Right? That's basically part of the definition of Dirac delta. The fact that integral of delta 4 over y just gives you phi of x. Right? That's why you have used the fact that this is the Dirac delta. Right? And then you don't need to use the relation between Dirac delta and Kronecker delta. Is that clear? Okay, just to learn the tricks, let's evaluate something like this. Delta delta phi of x of integral phi of y square dy, d4y. Okay? You can use chain rule. Of course, this is integral over y. That's like a sum over an index, right? So delta delta phi you can take inside. Okay, so this is integral d4y delta delta phi of x of, let me write this, phi of y phi of y. Okay. So this is integral d4y. The first one will give you a delta 4 of y minus x phi of y plus phi of y delta 4 of y minus x. So this is nothing but 2 integral 2 phi of x. Is that clear? Okay, you can try to consider more complicated examples and try to see how these derivatives are evaluated, right? Suppose you have a derivative, del mu of phi y, del mu of phi y, right? It's the same principle. The del mu, of course, del x, y mu has no commutes to delta delta phi x, right? That just, y is just like an index. So put this inside, right? Use this relation and evaluate the result. Okay, now we are going to apply all this in the problem that we had set up, okay, which is to evaluate the path integral. So what we'll do is to define an auxiliary quantity z of j. This is a function of j as integral d phi to the power I s plus I integral d4x gx I x. So this is a functional of j. Do you all agree? That if you are given any function j, that it gives you some specific weight factor, right? You carry out the partial integral over phi. After that, of course, there is no dependence on phi anymore, right? Phi is an integration variable which has been integrated out, but it can still depend on J. Now let's try to calculate this object, minus I delta delta J of x1 minus I delta delta J of x2 So J and phi are of course independent variables, so delta delta J you can take inside the integral. Okay, and apply, basically this is the only place where J dependence is coming from. Right? So you apply minus I delta delta J xn on this. So this will generate integral d phi e to the power I s plus I integral d 4x Jx phi x, okay. And then minus I delta delta Jxn will bring down phi xn. Okay. It's the same thing, but with differentiation with respect to J of x instead of phi of x. Okay, that will give you phi of x. Right? So it will bring down phi of xn minus 1 phi of x1. Okay, of course the order is irrelevant, right? Because these are just ordinary numbers. So this means that if we calculate 1 over z of 0 times minus I delta delta Jx1 So what happens here, that after you have differentiated, you say J equal to 0, so this term goes away. Okay. This is exactly the path integral you wanted to evaluate. Right? Integral d phi to the is phi of x1 up to phi of xn. Okay. But then you have to divide out by the same integral but without the phi's. Right? That's the normalization factor. That division is by J of 0, Z of 0. Right? Z of 0 means Z evaluated at J equal to 0. So this is integral d phi e to the is phi of x1 to phi of xn divided by integral d phi e to the is, which is what we have been calling the Green's function g x1 to xn. Is this point clear? Okay. So you differentiate. After differentiating, set J equal to 0. Right? That generates this with this term removed. Okay. And then you divide. Right? The division is by Z of 0. Right? Here now no differentiation in 0. You just set J equal to 0 and divide. Okay. So that gives the correct denominator. So this ratio is what you have been calling the Green's function. So this means that if you want to calculate Green's function in this scalar field theory, you have to calculate Z of j. If you can calculate Z of j, this contains information about all the Green's functions. Right? So one functional is what you have to calculate. So now the question is, how do you actually go about calculating Z of j? So how to calculate?
Zero by integral by.
Pardon? Yes.
Our D function is 0 by.
No, z, not z of 0. You have to differentiate t z of j n times, then set j equal to 0, right? And then divide by z of 0.
Divide by 0.
Yeah, you have to divide by z of 0 because otherwise you will not get this term in the denominator. Right? We need this in the denominator. For that you have to divide by z of 0. Is this okay? So to calculate z of j, okay, we are going to use perturbation theory. Okay, in principle you can try to develop non-perturbative techniques for doing this calculation, but we will be focusing on perturbation theory. Okay. So first evaluate this for free field theory. For free scalar fields. Okay, so let's call this z free of j, which is integral d phi exponential I So the idea here is that you consider the exponent. This is a quadratic function of phi. This is quadratic in phi. Both terms are quadratic in phi. This is linear in phi. So when you write in terms of discretized form, this is a quadratic expression plus a linear expression. So those integrals are normally easy to do, right? It's like a Gaussian integral, right? If you have a quadratic part plus a linear part, you first complete the square. Then do the integration over the square part, and then you are left with some quadratic expression in the j's. Okay, that's the way you will try to evaluate this. But we will do this at one step without having to discretize. Okay, in case you have confusion, you can always discretize and check that you get the same result. Okay, but we will try to manipulate things without discretizing. Okay, because that's what you have to learn to. I mean, if you really want to manipulate quantum field theories, right, it's difficult to always go back to a discrete form. Right? But that's not necessary. You can actually learn to manipulate the continuous integral form, okay, keeping in mind that the definition really requires discretization. Okay. Now, one point which I didn't mention, but let me mention it now, is that we will assume that whenever you have things like this, we can freely integrate by parts. Okay. You can justify this in many different ways. For example, for the space direction, right? How can you integrate by parts in the space direction? You can assume that phi of x falls off to 0 for large x, right? That's a boundary condition you choose on phi. Or you can assume that you have a periodic boundary condition, right? If you put it in a periodic box, right, then you can always integrate by parts, right? Because the derivative terms vanish. In the time direction, the reason that you can do integration by parts has to do with the fact, as you saw, that the result that you have derived here, right? If you go back to the quantum mechanics, right? We started with the expression where you had a q prime t prime at one end and q double prime t double prime at the other end. Okay? But you really never had to say what q prime and q double prime are, right? The final result, after you took the ratio, become independent of choice of q prime and q double prime. right? We could have taken q prime and q double prime to be anything that you like. So that q prime and q double prime are the analogs of the initial value of phi and the final value of phi, right? At minus t and plus t. So you can always choose your boundary condition so that initially and finally the phi is 0, right? So using that, so essentially the idea is that since the result doesn't depend on the initial and final values of phi, right, you can always assume that the boundary condition is such that the boundary terms can be ignored. Okay, take phi going to 0 as you go to plus minus infinity in time. Okay. So using that, we will justify integration by parts. Okay. So if we do that, then we can rewrite this as integral d phi exponential I half phi of x box x square x plus I g of x. Is this clear? I just integrated this by part. Okay. Box x, let me define it. Box x is del x mu, del x mu, or let me write it x mu, eta mu. Okay, the minus sign basically become plus because you integrate by parts.
I guess there's no I inside that jx.
Yes, and the I will be outside. So now I claim that this is equal to I by 2. Where g of xy is defined by so this is a Green's function. Okay, I'll prove that this is equal to this. Okay, basically the exponents I have to check that whatever I have written in the exponent is the same as what it was there here.
I by 2 is not there.
This is this one.
Yes, yes.
I by 2. I think the point is because there is an overall factor of I think the I by 2 is still there. We'll see what happens. Because you see, when you Okay, let's go ahead and see what we get.
Sir,
Yes.
sir, this after this curly bracket, this is multiplied. This whole thing.
After this curly bracket here,
Yeah. It ends then the second line.
yeah, the curly bracket ends here,
Oh,
the first curly bracket,
yes.
right? Then you have box x minus m square, and that acts on the second curly bracket.
That whole thing is a factor.
This whole thing is a factor. The whole curly bracket, this box x minus m square acts on the whole curly bracket.
And before that, this.
Before that also, this whole thing is a factor.
Okay. Times this.
Yeah. So this times box x minus m square acting on this. Okay, and then you have to subtract off this piece over here. Okay, so let me keep this last line because that's what we want to show this to be equal to. So you see this, so basically what you have to use the fact that this box x minus m square on phi of x is just box x minus m square phi of x, you don't do anything here. When this acts on gxz, it produces a delta function, delta 4 of x minus z. So this integral becomes delta 4 of x minus z jz, so that's just g of y, g of x. Okay. So I can write this one as I by 2 integral d4x phi of x plus integral d4y g of xy gy, and then box x minus m square phi of x plus g of x. Minus I by 2 integral d4x d4y.
So gxy is defined by a box x minus m square then.
Yes, sorry. Yes, you are right. Box x minus x. Thank you. Is this okay? Right, I just applied box x minus m square on this. Okay, so let's now collect this term. The first term, I over 2 integral d4x phi of x box x minus m square phi of x. Okay, this of course is exactly this term. Right? Then we have just I by 2. How should we do this? This times this. Integral d4x phi of x dx. Right? There are 4 terms you have to pick up, right? This one multiplies this one multiplies this, and then this one multiplies this, and this one multiplies this. When this, you take this product, okay, you see this is under a d4x. Okay, so this box x term I can integrate by part twice. Box x is del mu, right? So I integrate once, it comes on and acts on g. Right? That's the only x dependent function here. I integrate twice. Okay. The first time it picks a minus sign, second time that minus sign goes away, so it becomes box x on g. Okay. Minus m square, of course, it doesn't matter, it's a multiplicative factor, you can put it there. Okay. So the second term, then the third term I can write as I over 2 integral d4x integral d4y box x minus m square g of xy g of y and then phi of x.
So this also requires the assumption that the derivatives of the fields also die away. I mean,
That's it, yeah.
if you do it
Yeah,
like this.
exactly. Right? Or otherwise you can do periodic boundary condition on time, right? You just identify q and q prime and then integrate over q. Or q prime and q double prime and integrate over q prime. Right? Then it's like imposing periodic boundary condition in the time direction, right? And then all the derivatives will go away. Okay. Finally, we have this last term. That's I by 2 integral d4x d4y d4x d4y then g of xy g of y g of x, right? This with this, and then you have to subtract of this because that was already there, minus I over 2 integral d4x d4y g of xy g of x. So now we are more or less done. You see that these two terms cancel. Okay, that's how you had this minus I by 2, this subtraction over here. Okay, it basically cancels the product of the last two terms. So these two terms cancel. This term is the same as this term. This is half of this term, second term. Right? And what about this one?
So first term is also half of the first.
Yeah. First term is half of, no, first term is the whole term because half is already there here, no? There is a half inside. So the first term is exactly the first term. Right? Here there is no half, so there is an I by 2 here. So I by 2 integral d4x phi x dx. That's half of this term. Okay. This one, box x minus m square gxy again is delta for x minus y. Okay. So that converts this jy to into jx. Right? Again I by 2 jx phi x. Right? So these two together gives you I times integral jx phi x, that's this term. Okay. So this shows that this one is the same as what I have written here. Is this okay? Oh, but of course this looks much more complicated than that one, right? Okay, so that, I mean, we better get some mileage out of this, writing it this way. Okay? The advantage here now is that I can define a new field chi of x as phi of x plus integral d4y g xy dy. Okay, the sum of these. Okay. This is also the same, of course, because there is a dummy integration variable. So then, and d phi, you see, these are just constants. Right? So if you make a shift in phi, if I redefine our integration variable as chi, okay, instead of phi, okay, these constant shifts do not affect the measure. Right? It's like x goes to x plus c, right? Dx is the same as d of x plus c. So I can write the path integral now here as integral d chi exponential I by 2 integral d4x chi of x box x minus m square chi of x plus minus I 1 by p. Is this clear? But now you see that we are more or less done, because ultimately what are you looking for? This is our z of j. Okay? The overall multiplicative factor in z of j doesn't really matter, because you will be dividing by z of 0. Right? So what you are after is the j dependence of z of j. Right? As long as you can extract out that piece, overall constants will just drop off. So here now we see that first of all this factor doesn't depend on chi at all. So this can be taken out of the integral. Okay? So I can write this as some normalization constant n times exponential okay, I can also write, and it's useful to write this as n exponential minus half where delta xy is I times gxy. Is this clear? So basically this is all you need for free field theory. Okay, this is our z of j, and now any Green's function that you want to calculate, okay, you just have to differentiate with respect to j, and at the end set j equal to 0. Okay, for example, if you want to calculate g x1 x2 2-point function, this is given by 1 over z of 0 times minus I delta delta g of x1 of z of g. Okay? At a eventually so what will you do? First of all, you see that minus I plus times minus I gives you a minus 1. Let's first apply delta delta g of x2 on this. Okay? What will you get if you apply delta delta g of x2 on this? Let me do it in 2 steps. So 1 over z of 0 so this one, sorry, let me forget about the minus. Okay, there is an overall minus sign. Delta delta g of x2 on this will give you n, okay, let me write the factor first, minus Is this clear what I did here?
So there will be no half, means because you can integrate over any of the j, right? When you take you can differentiate over any of the j when you take differential with respect
Yes.
to del del j.
Yeah, but I have taken sum of two terms.
Oh,
Right? That here I have differentiated the second term,
okay.
j of y, right? When you differentiate j of y, you get delta of y minus x2, right? Delta of y minus x2, so that sets the that sets this y equal to x2, right? That's why you got delta x x2, right? And then when you differentiate with respect to the first one, you get delta of x2y. Now this delta j of x1 has to apply on the whole thing. Okay? So you can either apply on this, or you can apply on this. Okay? But after that, you have to set j equal to 0. Right? So if you apply the derivative on this, right, you will get some more factors of j. But those will vanish when you set j equal to 0. Right? So if you want to get a non-vanishing answer at the end after you have set j equal to 0, the only choice now here is that delta j of x1 has to apply on these j's. Okay. So this gives you 1 over z0 times minus half delta x1 x2 minus half delta x2 x1 times this n.
And the minus also.
Minus, yeah, so what are the minus outside? Thank you. Okay, now I have already set j equal to 0. Okay, so this exponent has gone away. Okay. And z0 of course is n. So this gives you at the end, this minus sign cancels this minus sign, so this is half delta x1 x2 plus delta x2 x1. Okay, actually delta x1 x2 and delta x2 x1 are the same. Okay, this we'll see in a few minutes. Okay, but because of this, I mean, we have not shown it here, so I have written the sum of two terms.
So can you say this line again?
This line,
Yeah, from
z of 0, y, z of 0 is n.
no. This minus.
Oh, second.
There,
Okay.
there.
Yeah, so there is a minus sign, this minus sign is minus sign. Okay. Now delta j of x1 has to act on as a derivative, right? There is j dependence here, as well as j dependence in the exponents. So these two terms are the ones where you have taken the delta j of x1 of these. Okay. So that gives you delta for x minus x2, sorry, x minus x1, right? That gave you delta x1 x2, right? When delta j of x1 acts on this, you get a delta for y minus x1. That gives you this one. Okay. So that part is clear, right? Okay. Then delta j could act on this. Okay. But after it acts on this, you are supposed to set j equal to 0. Right? So if it acts on this, it will bring down one more factor of j. This quadratic in j, right? There is already two factors of j, the factors of j here. Right? So the second term where delta j had acted on this, right? It's non-zero, but after you set j equal to 0, that term will go away. Okay? That's why I didn't write that term. Okay, I can just stop at these two terms that I have written here. Is this point clear?
So this g in the exponential and this g are different, right? So delta is
Oh yes, that's true. Well,
this is the free.
yeah, this g, maybe I should have not used the same symbol. Anyway, once I've done it, you cannot do much. This g is different from that g. It's not that different. I mean, there is a factor of I think, between the two, right? Because this g is delta, we see, right? This is g x1 x2 is half delta x1 x2 plus delta x2 x1. Right? So it's almost that g, except that between g and delta there is a factor of I. Okay, but a priori this g, yes, this g is different. Okay, this g solves the differential equation. Right? We are not going to, yeah. solve this. So maybe I'll since at this stage let me put a G tilde. Okay, of course I cannot change the rest of the steps, but this is at least I can put a G tilde here. Okay, so all the definition is still there. Okay, delta is I times G tilde. Okay, so now let's go to the calculation of G tilde satisfying this. Okay, because this shows that once you find G tilde, you have delta and then this two-part function is given. And in fact, you can also easily verify that higher point functions can be similarly calculated. Okay, maybe we'll do it next time, higher point functions. Right? It's the same principle, right? If you have a 4-point function, you differentiate 4 times and then you have to set j equal to 0. Right? So that basically means that you bring down 2 factors from the exponent down, okay, and then you don't have to worry about any more derivatives acting on the exponent.
Sir,
Yes.
in the end we will have this term in the beginning, the last line.
This term?
This term, yeah.
Oh, this term I have called n. Right? See, n is, the important point is that n is independent of j. Okay? So I have called that n, and that n will cancel because there is a 1 over z0 sitting here. Right? So this term will go away. Right? Because it's independent of j, whether you set j equal to 0 or not, it's the same value. Okay, that's what makes it cancel. Are there other questions? So let's try to now solve this. Okay. So we'll solve this by going to the Fourier space. Okay, so we'll take G tilde xy as integral d4k over 2 pi to d4. Let's call it some function of k. I have taken in anticipation that G tilde xy should depend only on the difference x minus y, because the differential equation you can see on this side depends only on x minus y. Okay, so you can assume that G tilde is a function of x minus y only. So I have taken it as a function of 1 variable or 4 variables, so the 4 components of x minus y rather than 8 variables, and expanded in the Fourier basis. So now this equation takes the form of delta 4 of x minus y as integral d4k over 2 pi to d4 f of k, and then the box x minus m square acts on c to the I k dot x minus y, and that's what the x dependency is on that side. So that gives you minus k square minus m square. Why minus? This minus comes because the I comes down twice. Right? That gives you minus. Right? Otherwise the box x is just k square. Is this okay? But of course you know the delta function has a representation which is integral d4k over 2 pi to the 4 e to the I k dot x minus y. Okay. So if you take the inverse Fourier transform on both sides, you basically get f of k as 1 over minus k square minus m square. So this tells us that G tilde xy is integral d4k or delta xy the minus k square minus m square is k0 square But now you see that we have a problem because this can vanish. You are integrating over these 4 real variables, right? But along the integration axis, there will be points where this vanishes, right? Where k0 is square root of k square plus m square. Okay. So this integral that I have written is not well defined, right? So now the question is what to do with these singularities, right? How to define the integral around the singularities. Is this clear? So to see what to do with these singularities, you have to remember that somehow in this whole analysis we have ignored one subtle point that we discussed in detail yesterday, okay, but today we forgot about it. Okay. And the subtle point was the fact that the time axis, okay, cannot be taken to be along the real axis. That it has to be tilted. Okay, it has to be tilted because otherwise the path integral doesn't reproduce the vacuum expectation value of time order proto-operators, right? In order to reproduce the vacuum expectation value, you have to tilt the time axis. Okay. We give 3 different ways of looking at this. Okay, one is tilting the time axis a little bit. The other one is tilting it all the way to the imaginary axis and define the result as analytic continuation. Okay. And the third way, which is slightly independent but which does the same job, is to keep the time axis along the imaginary along the real axis, okay, but somehow ensure that the excited states, okay, acquire a small negative imaginary part in that energy. And that will also do the job. Remember this? Right? So any of these we have to implement, right? But we have not implemented either of them. Okay, we have just taken energies to be all real, right? We have not, meaning the original action is real, right? So there is no way the energy can become complex. Okay? And you have taken the time axis to be along the real axis. Okay? So now let's try to repair this.
So is this like we see that it is not well defined here because we didn't do that?
Exactly. It's not well defined here because we started with an expression which is ill defined, right? Which is not because in terms of path integral it has an oscillatory exponent, right? It has no damping factor, right? In terms of the, even going backwards, in terms of the what you are computing, right? We have seen that in this the t goes to infinity limit that you have taken, right, is sensible only after you have tilted the axis, right? Because only in that case that only the ground state contributes and all the excited state contributions go away, right? Otherwise it will be a very highly oscillatory object, right, if you don't tilt the time axis. Because from all perspective we see that we are not supposed to get a well-defined integral, right, unless we tilt the time axis or put a imaginary part to the energy, and that's what is showing up eventually here. Okay, so let's try to go through these methods one by one. Okay, so we'll start with 3, which is easiest to implement. Okay, which is somehow introduce a small imaginary part, a negative imaginary part to the energy. Okay, to the excited state energy. And that we can do by simply replacing m square by m square minus I epsilon. Okay, this we discussed yesterday. Okay? Because once you replace m square by m square minus I epsilon, right, the energy of excited state, say single particle state. Okay, I'm assuming now that you know from your QFT1, right, what the spectrum of this free field theory is, right? It has single particle and multi-particle states. So single particle states will have energy square root of p square plus m square minus I epsilon, right? If it carries momentum p. Okay, multi-particle states will just be additions of terms like this. So this is square root of p square plus m square minus I epsilon 1 over 2 square root of p square plus m square. So you see that indeed we have a small negative imaginary part in the energy, right? If you replace m square by m square minus I epsilon, you can suppress contribution from excited states. Okay. And here you see that once you replace m square by m square minus I epsilon, the pole gets shifted from the real axis. Okay. And then you can in fact define the integral without any problem. Okay. So then this gives you delta xy as I integral Is this okay? Okay, now let's suppose we didn't do this. Okay, we want to keep our m real, but we tilted the time axis. Okay, so how did we have to tilt the time axis? We will take t to be tau times 1 minus I epsilon. Right, tau is real, right? You have to take multiply this by 1 minus I epsilon. That's what tilts the time axis to below the real axis on the positive side and above the real axis on the negative side. Let's see what effect does this have on the action. So if you look at the action, which is integral d cube x dt. Okay, now let me write the terms explicitly. So this will go to so because you are changing dt to d tau, you get a 1 minus I epsilon factor from here. Okay, you could have this is what I am doing here is equivalent to making the delta into delta naught times 1 minus I epsilon, right? I am just writing in the continuum language. Okay, if you don't like this, you can go to the discrete form. Right, and just replace delta by delta naught times 1 minus I epsilon, it is the same effect. So d tau, so now you get, here you see, there will be 1 minus I epsilon multiplying it from top, okay. But del t is 1 over 1 minus I epsilon squared times del tau, del t, sorry, the second, del t is 1 over 1 minus I epsilon times del tau, but it will square, okay. So you get 1 over 1 minus I epsilon times half del tau phi square minus half 1 minus I epsilon that phi square minus half 1 minus I epsilon m square phi square. Is this clear? So let's see what its effect will be on the propagator. I should have said this delta xy is what is called the free propagator. So delta xy into I integral d4k over 2 pi to the 4. First, there is k0 square term, right? Okay, k0 square minus k square minus n square. So, can you guess what will change? Because of this 1 over 1 minus I epsilon, right? What is going to change? So, k0 square will be multiplied by 1 over 1 minus I epsilon, right? Because the box operator, right, will have a 1 over 1 minus I epsilon now. So, this will be multiplied by 1 over 1 minus I epsilon. And these two are multiplied by 1 minus I epsilon. So, this I can write okay, let's take epsilon to be small. So, k0 square minus k square minus m square, and then this I can write as plus I epsilon k0 square plus k square plus m square plus order epsilon square, which you don't care about. Is this clear? So, net effect is to add a small positive imaginary part to the denominator. That is the same as this. Okay, the fact that this is epsilon and this is epsilon times this really makes no difference, right? It's a question of which way the poles get shifted, right? On the real, they are on the real axis to begin with, so that they are going below the real axis or above the real axis is all you need to know, right, to be able to do the integral, right? And for that, it's enough that it's just a positive imaginary part. Okay, so you might as well use this I epsilon, which looks simpler. Is this point clear? Okay. We can also try to use the third method, which is analytic continuation. Or what I had called yesterday the second method. So, in the analytic continuation, what we do is we replace t by tau by u, right? But u is some number in the upper half plane. So, by following the same line of argument, we can check that delta xy, okay, let me now add the subscript u, okay, because of course it will depend on u eventually, right? At the end you have to take the u goes to 1 limit. So, this is I integral d4x, d4k over 2 pi to the 4. So, here you will get k0 square by u minus k square plus m square times u. Okay, basically the 1 minus I epsilon. Is that? No, sorry, it's the other way. It's the other way. Okay, you see that here dt gives you tau by u, right? D tau by u, right? But this one brings our u square in the numerator, right? So that's why this is multiplied by u. This u inverse just comes from the fact that dt is d tau over u. Okay. So we claim that this procedure should make things analytic in the upper half u plane, right? Let's see if that is true or not. Upper half u plane means u equal to r e to the I theta, right? Where r is positive and theta runs between 0 and pi. Okay, so let's evaluate the denominator. So you get k0 square by r. U I can write as k0 square r cos theta plus I sin theta. Maybe I write something else. Yes, I write it here. So we get k0 square. U is r times cos theta plus I sin theta. Right? Minus k square plus m square divided by r times cos theta minus I sin theta. Okay. So let's separate out this real and imaginary part. One is k0 square r cos theta plus minus k square plus m square over r cos theta plus I sin theta times k0 square r plus 1 over r times k square plus m square. Is this clear? And now the important point to notice is that this factor, the imaginary part, never vanishes in this range. As long as this is not equal to 0, as long as theta lies between 0 and pi, and r lies between 0 and infinity. Right? Because this is of course strictly positive, right? And sin theta is also strictly positive in this range. Yes, it never vanishes. Which means that in the entire upper half plane, this integral is completely well defined. And this integral, the integrand has no singularity. Is this clear? Not clear? So the integrand never becomes infinite, right? Because the denominator is always finite. Its imaginary part is non-zero. And that means that there is no problem in defining the integral. And that will be an analytic function of u. Right? Because it depends only on u and not on u bar, right? So there is nothing which can break the fact that it depends on u. Okay. So this shows that the propagator defined this way, okay, is an analytic function of u over the entire upper half plane. Okay. And because it's an analytic function of u over the entire upper half plane, you can choose to define it, for example, on the imaginary axis, okay, which is u equal to purely imaginary. So if u is I, right, that corresponds to theta being pi by 2. Right? In which case this term just goes away, right? And the propagator becomes purely real, right? Because this I cancels that I that comes here, right? It just this is what we call the Euclidean propagator. Okay, if u is taken to a purely imaginary, should I write it down? Maybe I should write it down. So for u equal to I, for example, for u equal to I, delta u of xy is
What the minus?
the minus sign, let's see. No, there's no minus sign. It's just this. Okay? Because there's a factor of I over here. And I just pick the denominator for theta equal to pi by 2.
There is no I, right?
Effectively there's no I, right? There's one I in the numerator and then that cancels against I in the denominator. So this is what you normally call the Euclidean propagator. Okay. And because this full propagator is defined over the entire upper half plane, right? The result for u goes to 1 is just an analytic continuation of the result from the u equal to imaginary axis. Yeah, so that's another way of defining this delta. Is this clear?
So why you don't care about the real part of this denominator?
Well, we of course care about the real part, right? For u equal to I, the real part goes away because theta equal to pi by 2, right? For generic u, of course, we care about the real part, but what is important is that as long as the imaginary part is non-zero, the real part can vanish, right? Because there is a minus sign between the two terms. But as long as the imaginary part is non-zero, right, the whole thing is non-zero, right? So then there is no problem in defining this integral, right? Even if the real part vanishes, right? As long as the denominator is non-zero, you can continue to define the integral, and that's what is needed to show that it's an analytic function of u. If the denominator vanished, both real and imaginary parts vanish, then the integral becomes ill-defined, right? And then it's not clear that it's an analytic function, right? Where at that point it's not even defined. But as long as the integral is well defined, right, you know that it's an analytic function because there is dependence only on u, right? There is, you have not introduced any u bar dependence anywhere.
So this x minus y in the exponential will also be scaled by a u kind of, if you get an imaginary thing, right?
Only the
No.
k that come from box.
Yeah, k0 by definition is the Fourier transform variables of tau. See, we don't want to play around with k. K is real, right? So k, see, what I did here is that I rewrote tau t as tau over u, right? Tau is a real variable, right? Then I picked up explicit factors of u, right? And then del tau would produce an ik0.
Right. So this x minus y has x0 minus y0, right?
Yes, this has x0 minus y0, that's right.
So that will pick up a 1 by u if you break it, right?
Well, that depends on,
If you're
yeah. So x0 you have to think of as tau 0. Tau. You see, if you think of x0 as t, you are right. Okay? But I am thinking of x0 as tau. Tau is real, right? See, in the exponent, you don't try to introduce any imaginary parts. Right? x0 and y0 in this language corresponds to just tau. Right? Tau x and tau y, which are all real. Right? That's why, yeah, what I have done is that I have rotated, I have replaced t by tau by u, right? And then rewrote the whole action in terms of just tau, d tau, tau derivatives, u factors explicitly taken out. Right? So now tau is basically playing the role of t. Okay, once you have taken out the u factors explicitly, right, I am just treating tau, which is a real variable, as the way we had treated t earlier.
So that is the Fourier transform variable.
That is the Fourier transform variable, exactly. Right? If you want to rewrite in terms of t, yes, you have to introduce this u. Okay. But normally you don't do that, you work with tau. Okay. Where at the end, of course, when you take epsilon goes to 0, you remember that we had these ti's as tau I times 1 minus I epsilon, right? Okay. Eventually you are going to take epsilon to 0. Right? So all the ti's will become tau i's. Okay? So in the exponent, because the limit exists, right, it doesn't matter, okay, that you can continue to use tau I. Okay? The place where you have to actually put in the exponent, the epsilon, is where it's ill-defined without the epsilon. See here, whether you put the epsilon or not, it doesn't matter, right? At the end, when you take the epsilon goes to 0 limit, that is going to go away. Right? Here it matters, because here, if you put epsilon equal to 0 from the beginning, the integral is not even defined. Right? That's why you have to put the epsilon explicitly here. Okay. Whereas in the exponents and all, this x and y, x0 and y0, you can just think them in terms of tau, okay, and continue to define the integrals. But at the end, when the epsilon goes to 0, tau and t are the same. Is this point clear? Right? If you had put some exponential minus epsilon times x0 minus y0, right? You can put this factor, but at the end, you have to take epsilon to 0, right? And then those factors will go away. Other questions? Yes.
Sir, I mean, do we always require the ratio zj by z0 or?
That's right, yeah. Because all calculations, right, require the ratio zj over z0. Because as you saw, the Green's function is the expectation value, the vacuum expectation value divided by the norm of the vacuum, right?
Actually, what I am thinking that we are using the at space boundary we can use that periodicity.
Yes.
But in time boundary, we are taking that in the space of fields functions. We can arbitrarily set our field configuration at minus infinity
right,
and
yes.
plus infinity, and we are using that to be 0.
Yes. Well, either we can think about either using it as 0, or you can say that you are using periodic boundary condition.
No,
Like
at time boundary.
Yeah, even a time boundary. So you had q prime. Q prime t, q double prime t double prime, something, and then q prime t prime, right?
Yes.
The final result didn't depend on q prime and
The
t double.
configurations at t.
Yeah.
And t
So both in the numerator and denominator, right? What you can do is you can set q prime equal to q double prime and integrate over q prime. Okay. That will be like introducing periodic boundary condition, right? At minus t and plus t, you are using the same q, but you are not specifying what that q is. You integrate over that q. Okay. So you could also impose time periodic boundary condition on the time coordinate, because at the end, in the capital T goes to infinity limit, all of those just go away. That the dependence on what boundary condition you have chosen simply go away in this limit.
Because of the ratio or just even?
Because of the ratio. Because both in the numerator and denominator you will get integral dq q omega q times something, right? Okay, so as long as you do the same operation both in the numerator and denominator, this will disappear. Yeah, that's why in the time boundary you don't worry too much about what boundary condition you are putting.
What about R in the final expression?
What about?
R smaller. From the beginning we are.
Well, I mean, the point, the smaller you can put in, but what I'm saying is that at the end, of course, you have to take u to 1, right? So what this shows is that for any value of r, smaller, right, it's free from singularity. Right? That's what is used to show that it's an analytic function of u. Right? If you want to calculate u at some particular value on the imaginary axis, you have to put the corresponding value of small r. But at the end, the physical answer is obtained by taking the u goes to 1 limit. Okay, so they are, of course, so they have put in the smaller or not, doesn't matter. Right? But you need the smaller if you want to actually define this as a function on the imaginary axis, because then you can analytically continue back to the real axis. Right? If you know for one particular value of u, that's not enough. Right? To be able to get the result on the real axis, right, you have to know the result at least on one dimensional line. That's the theory of analytic continuation, right? You have to know on a certain interval. If you know the value of the function in a certain interval, then you can analytically continue. So you have to, that's why you needed the small r, right? If you had just known the value at u equal to I, you couldn't have done the analytic continuation, right? But as long as you know it for a certain range, you can do the analytic continuation to the real axis. But at the end, there is no dependence on small r, right? Because you are coming back to u equal to 1. Any other question?